My name is Christian. I'm with Sumo Logic. I started a company together with my buddy Kumar in 2010. I'm the CTO over there. At Sumo Logic, we're doing cloud-based, basically log management. I was previously a server guy and a chief architect at a company called ArcSight from 2001 onwards and up until 2010. At ArcSight, we also dealt with logs. We dealt with logs for security. ArcSight was a security information and event management system. The point here is mostly around, hey, most of my professional career in software anyways, I've spent dealing with logs, with machine data. And so I've been around the block a couple of times, but times are changing. ArcSight was ultimately, in late 2010, sold to HP. HP paid a nice little premium on top of the price on the street, so thank you very much, HP. I got a nice car out of it. And then I see this. That must have been sometime last year. And what that tells you is that I'm a dirty liberal, and I look at NPR tweets. No, actually, it's about HP. So this showed up in my tweet stream, and a couple of minutes later, this showed up. The point here is that things really are changing. We're going to talk about a couple of things that we have changed while building a log management, log analytics, machine data analytics service. So here's the agenda for today. It's a full hour, so I'm going to be rambling, until you guys flee the room or until we get kicked out. I'm going to start talking a little bit about logs. What is that log thing? Then I'm going to talk a little bit about why we actually went and built this service. We talk about the architecture of the service. And then I thought I'm going to talk a little bit about what we are doing, because, hey, it's in the cloud and all of that, around automation, because it's a very big part and a big change to how we've built stuff before. I'm talking about a couple more things, and then ultimately we're going to wrap up, and I'll have 2 MBA slides. So, introduction to logs and logging. Actually, one thing before we get into this. It is quite possible that my voice is going to cut out at some point. Fortunately, picked up while traveling some sort of bug last week, and my throat is not in good condition. So I have tea with honey here, and these things. So I hope I don't have to take them. Anyways, so maybe if my voice cuts out, it's better for you. Anyways, so we'll see. What is machine data? Well, I said logs, talking about log management, but really sort of the term that has developed in the last couple of years is machine data. So what is machine data? I'm not going to read that back to you. You can read it yourself. It's really about machine-generated data versus human-generated data. So here's a fun little pop quiz. Monash and Abadi, based on those definitions, who do you think is the academic? Anyways, so this is a topic that data people are talking about. This is a new kind, it's not really new at all, but it's data that is now coming into the spotlight again. What are examples of machine data? Well, basically logs, all the stuff that your computer and your network kind of spits out. Other things, satellite and telemetry data. There's good uses for it, and then there's better uses for it, like espionage. Location data, RFID chips, container ships moving around stuff. All of that produces data, various sensors, medical devices, actually. So machine data is, becoming more popular, and the spotlight is being shown on it even more so than just when it, just to the log subset, under the context of the Internet of Things, and everything's connected and everything is spitting out information, right? So anyways, so that's machine data. Logs are a kind of machine data. Given that we are at this conference, I think I don't really have to explain, that I think you should have, probably coming into this room, you should have a general notion of what a log is. I have some examples as well. We're talking about these little bits and pieces of text, little poems that programmers write to themselves, in debug statements. And they can actually be quite useful. if you can manage them, because there's a lot of information there that you won't get from metrics and other things like that. So this is how my screen looks sometimes. We have a very decentralized multi-cluster system. So anyways, those are all logs. And they won't go away. They go. All right. Another way of putting it, there is a lot of information in logs. We have used the analogy of Twitter. So it's basically like Twitter for your infrastructure. Just think about all of your little machines. They're sitting there in their racks, and it's getting hot, and maybe the other guy's an asshole. Three switches down, and so forth. So things go and basically talk constantly about how they're feeling. And another way to look at log analytics is it's almost like sentiment analysis for machines. The point is that you have this data already. It's basically free. Your applications, your infrastructure, your networks, they will spit this information at you. So you can either let it drop to the floor, or you can take this data, and it has a tremendous value, and get the use out of that. So don't forget to manage and analyze your logs. Otherwise, Catzilla will sink your ships, right? So we were running infrastructure that's we don't want that. How does a log look like? I'm going to run through this real quick. This is just a sample log from one of our systems. Of course, there's a timestamp in there. If you're responsible for logging in your company, please put the time zone there, because otherwise we don't know what time it was over there when the damn thing happened, okay? Log level, that's from syslog, info, debug, error 1, that kind of stuff. What we like to do as we run an application that sort of runs on many different machines, in the AWS cloud, we like to put a nice human-readable host name in there. That can help later with the analytics. So we know this is the first front-end node in this particular case. If you can, put a little code location there so people can, if they look at the logs later on, find a piece of code that actually generated it. The other thing that we found very interesting and that we're actually doing across the entire system is put an authentication context in there. So usually what happens if you build systems today, you have these multi-tier sort of things where there's some request coming in, and then there's some orchestration going on, and we talk to some other backend system that gets you some piece of the data, and then you talk to yet another backend system, maybe with the result of that, and then that goes and talks to another guy. And so these requests basically span all the layers, multiple tiers of your application. And in between, you make RPC calls or you use messaging or whatever. It's fairly easy to keep around some sort of contextual information, just stick it in a hash map or something, about who actually made the call coming into the system initially. So which user it was, maybe you have a user ID in there, so that kind of stuff. And then when you call into the deeper layers of your application where, well, now I could just make the call, but I don't know anymore on whose behalf that call happened. And then that can be very unpleasant later if you need to pull this all out and put it back together. So put the authentication context there. That has helped us a lot. And then the rest of it, use some sort of key value pair format. Don't write haikus. I mean, they're funny, but if something really goes down and you need to decipher what went on, then that gets old pretty quickly. Long-standing discussion, what kind of format should I use for that? Can somebody please write a standardized format for that? Yes, people keep trying. Just look at those mailing lists. It's intentionally good, but it's very, very hard to get right. So this is actually something, this is in fact, I actually used a log that I wrote myself, so I have a fairly verbose key value pair syntax here. We have also now started to use JSON a lot. So it's pretty easy to make, and it's also fairly human readable. If you absolutely want to, you can put XML in your logs, but I will think less of you. Most tools, whether it's ours or the other players in the space, will have a way to sort of figure out the key value pairs automatically, so you don't have to be super precise there. It doesn't have to be all RFC-based. Okay, so now we have seen, on a very low level, what does a log look like? What are some use cases that we find interesting? Availability and performance. Clearly, you're running some sort of system. It's got to stay up. And if it actually goes down, then you need to find out quickly. You want to make sure that your requests are processing in time and so forth, right? And yeah, you can look at your web server, maybe you have some metrics instrumentation there, but often the problems are deeper in the back end. And these things are not usually, there's no sort of common way to get metrics out of that. So just put it in the logs and use the log analytics tool to pull that back out. The point here is that if your shit goes down or your shit doesn't perform good, you are losing money. And if you're responsible for running that stuff and the company keeps on losing money, then you will be out of a job eventually. Another use case we find very interesting, application release. Even before you release an application, you have staging environments. Get the visibility, look at what's actually going on, push new code, figure out, hey, what exceptions are in there. Previously we had like one little web server and then we just looked at the error log and that was all there is. But today we're building these large distributed applications. So get everything into one place and take a look at it before you ship it, before you push it to production. If you do deploy, look at what happened before. Try to find a way to sort of quickly find a baseline of your behavior. Count of error by module. For example, there's some very simple things that you can do. Run that again after deploy. See what changed. You will oftentimes be quite surprised. And then, of course, security and compliance. Most compliance regulations have a part in them that talks about, hey, you need to put all the stuff in one, but you need to put all your logs in one place. We want to see who logged into your systems. You need to know that. You need to do these kinds of analysis. So that's a security use case. Again, that is, there's literally people going to jail if you don't do that. Quick proof points, across these use cases. We can actually help people. We've helped people like Apogee, Inc. Mobility, saving about $500,000 annually in not spending time in a war room, but using a centralized way of looking at their logs, and so forth. So here's an interesting observation that we've made over the years. Machine data and logs are actually big data. Volume, velocity, and variety are all there. We said at some points when, after having a couple of pints, logs are the original big data. Our system, just our system alone, generates about 1 terabyte of logs per week. We have customers that generate 1 terabyte of logs per day. So, if that's not a lot of data, then I don't know what it is. And it's more data every day, obviously, so today, and then that grows very quickly. Machine data occurs in real time, and it's time-stamped. So, you need to be able to pick it off the wire as quickly as you can. There's no point in processing it tomorrow. And finally, the variety bit is, hey, it's actually unstructured, or for those of you who are a little bit more anal, it's actually polystructured. The fact is that logs actually have a structure. Whatever the guy thought that actually wrote the log line, that's the structure. But every log line usually has a different structure, and hence polystructure. That's a term that's coming up these days. So why are we building this service? Because we need to evolve. We need to evolve, and we need to deal with the fact that when we are dealing with logs and machine data, we actually have a big data problem. And the legacy products fall short on that. Having a software and handing it over and expecting you to scale it on your own leaves you with the hard part. So I'm not actually going to go through these all in detail. We have enough sales guys running around at the booth that will tell you this in excruciating detail. There is a lot of truth to that. We see this with all the customers that we're working on. The whole idea of putting the stuff on-prem and letting customers scale it themselves, there's just too much data. It's hard to sell clusters to people. Letting people cluster your own software if you're a commercial vendor is really hard. So we built this company on top of AWS from the very beginning. At some point, Kumar, my co-founder, and I We went to Werner's talk at Stanford in 2008. Some of you weren't even born back then. And maybe the first parking lot discussion about sort of this hey, what does this mean, for us, happened like literally that day. We walked out of there realizing that what AWS did, and it hasn't really changed, and it's still the core point for me why I like this thing so much. It is a data center as an API. I'm a software guy. I know nothing about data centers. But if I have an API, then I can, that feels a little bit more comfortable. Massive power up, with just a bunch of devs, right? Build a large scalable system, bunch of Game Boys probably. No, you need real power, and AWS gives us that. We are entering an existing market. Market is proven. We have to go in there, and we have to grow fast. There's competition. Some of it is pretty big. We have to both catch up and differentiate at the same time. We really have to build the product very quickly. And we're dealing with big data, so people will send us a lot of data, so we have to be able to scale it quickly. And we now not actually have to only scale to how much data a single customer is sending us, but this is a multi-tenant system, obviously. We have to build it so that it scales to all customers. So elasticity, quick turnaround, being able to bring up a staging deployment, with a bunch of API calls, all of that. That really makes a big difference for us, makes a big difference for our agility to build a good product very quickly. And then, of course, the data is important. There's compliance issues and so forth. And if you've ever tried to architect for a SIM or some other kind of log management system, an HA or even DR solution, then, it's just a pain in the ass, basically. It's very expensive. You're going to get your hair's going to fall out. Previously, these solutions were built such that there was a couple of machines that were like sitting there, pulling out all the information from your on-prem stuff, sitting in your data center. Everything went into some sort of server or appliance, a lot of additional infrastructure that you needed to put there. What we're doing today is, well, it's just one system. It's in the cloud. And all we need to do is make sure that the data comes to us. How did we build the system? What is the architecture of the system now that we've hopefully made clear why we went with AWS? Our development approach. We decided to use Scala. We're Java guys. We got bored of Java, so we were like, hey, why not bet the company on a totally new language? You should definitely do that too. The idea is, it is a big distributed system. So let's make it so that it's modular. Let's make it so that the functionality that belongs together goes together into a module, cohesive, low coupling between the modules. In our case, we use Maven. There's many opinions on it. It works with a little bit of pain. Layer those modules into applications. Share underneath, ultimately build out applications. Applications have very narrow responsibilities. Link them together via messaging or RPC. Basically build an internal service-oriented architecture. Here are the basic concerns that our system has to deal with. We have the data ingestion part, and we have the data analysis part. And there's this interesting thing that's sort of in between, which we call continuous queries, where it's really not that separated. The data comes out, and then the results update automatically, so that's why I put it in the middle. These concerns on our end map to clusters. This is our internal language that we are using. I just talked about the fact that everything's modularized, and we kind of layer the modules, and out pops a bunch of applications. Each one of these applications gets deployed many times as part of the same cluster. So it's basically a scale-out architecture. But not just once, it's like on each layer. Everything's deployed across multiple instances. Yeah, well, that we could have probably figured out ourselves. Availability zones, we'll just split it out. The instances within one cluster are mostly oblivious of each other. They receive requests from the upstream and respond to them, or they talk to something on the downstream. And we use both messaging where it makes sense, where we don't necessarily need to get a reply immediately. We also use RPC. Here's how the ingestion path looks like. There's this cloud thing, and then the requests come to us, they get received by a thing that's called receiver. We had this company that knows how to make the names for all of us, a naming company. You know about those? Never mind. The receiver takes all the information from the wire and batches it up, puts it on a bus, and then sends it to these other currently three processing systems. Quick drill down into the individual guys. The receiver is essentially an HTTPS endpoint that sits behind ELB. The data comes to us in a compressed fashion because logs are basically ASCII data, so you can compress it 1 to 10 easily, and you should, because it's saving you bandwidth. So we decompress, and then we do something that's very interesting and actually not that easy. We try to figure out what the timestamp is in the message. A log message without a timestamp is actually not that useful. So we have multiple ways of doing that. There's a little bit of machine learning going on, but there's also ways for us to simply supply patterns. And so over time, we've seen a lot of different timestamp patterns, and whenever we see one that neither the inference could catch, nor we had a pattern for, then we simply add that. We then aggregate the individual messages that are coming from the collectors per customer into blocks. And then those blocks get flushed to a message bus where then there's more stuff going on the other end. Then we act back to the collector. So all of that has to happen pretty quickly. So the receivers are to some degree stateful, but there's no state in there that couldn't be recovered, which is why I'm using this sort of funky language, statefully stateless. I need to find a better term for that, but anyways, that gives you the idea. There are many of those receivers sitting all peacefully next to each other, getting the data from the wire and doing what it says on the slide. And if you remember the picture earlier, stuff gets onto the bus, and then we send it. There's basically 3 consumers for each block of data. The first one is relatively simple. It's called raw. It processes the raw messages again. Very creative naming. We encrypt the message blocks. We use a different key for every customer for every day. And then we put it into S3. The block has an ID. That's the key name in the S3 bucket. And then we act back to the message bus and update a metadata system so we can actually find this data later on again. If you want us to, we can also give you a copy of that block as CSV. We just added that recently. So the raw thing is basically fully stateless, so that just scales out really nicely. Index is an interesting one. This is where the full text indexing happens. One of the things that these types of systems do is they take in all the ASCII data, shred it up, and index it. Full text index. It's like Google almost, right? And this is actually one way that you get back at your data. There's some search box, and you start typing, and the data comes back. So what happens here, again, we receive from the message bus. Then we cache it to disk temporarily and act back. So at that point, we know we have it received properly. And then, over a small window of time, we add the message blocks, individual messages, to a Lucene index. When it comes to search, especially if you're already a JVM platform guy, then Lucene really works really well. Lucene doesn't do anything like distributed, like real-time updates and so forth, but that's where we come in. Anyways, underneath it's Lucene. Couple of interesting things there is that you have to deal with wildly varying timestamps. The problem is that you cannot actually trust the timestamp that's in the message itself. Well, you can parse it, but then that doesn't necessarily mean it's the right timestamp. Machines are notoriously putting timestamps into logs that are either in 1969 or somewhere in 2040, or somewhere in between, completely random. They're almost never exact. Because we later on have to find the index shards for searches that go across different time ranges. We cannot bunch too many messages with too many varying timestamps into one shard, because then the actual overall time range that gets spanned by that shard is too big, and then we need to bring back too much data just to answer every query. So there's a bunch of really interesting things going on there to figure out how many index shards do I actually need to make. And based on the timestamps that I'm getting. Then we flush the shards to S3. We like S3 because once it's there, it really never goes away. Writing to S3 is very fast. Reading it back from S3 is very fast as well. Then we update the metadata database so we can find these index shards later for this customer. This one is stateful, cache to disk before hacking back. And then, if the node goes away, we still have the disk. We bring up a new node, attach the disk, and everything just continues. So the other thing that's in between is there, the third one is called continuous query. It's basically a streaming query engine. This is a real-time query engine if you want. The data goes in. There's a number of queries that are running some sort of aggregation. Count by your module, this type of error, whatever. As we are shooting the messages through the continuous query engine, these results will basically update in real time. And then on the product side, you can see that in the dashboard. So that's very cool. Notable things about this one is that, well, it's all in line. And the state of the queries, because these queries are obviously stateful. If you lose the machine that has all the state in memory for like 100 or 150 or maybe 1,000 queries, well, then that's really not that cool, right? Because now you lost all that sort of intermediate data. So we do sort of a checkpoint recovery mechanism there, and the checkpoints or the snapshots actually go into S3 as well. The analytics path again is driven from S3 via the query engine. There's this thing called service there, which provides our API layer. That's what the UI talks to, and that's also what you talk to if you use our API. CQ is continuous query. Again, we already talked about that. That one sort of sits on both sides. It talks to S3 if it has to recover snapshots, so that's mostly an availability thing. The query engine is interesting. It's a fully distributed streaming query engine, so every query that you do is essentially a replay of old data. In fact, it's actually the same engine that drives the CQ thing. That's something that we're very proud of. Probably matters to exactly 2 people in the world, but we're really proud of that. What happens is that your queries start with a search expression, like you would in search in Google. That selects which messages you then want to further process. And so you can sort of pipe these operators together, and they can do extractions, they can do aggregations, and so forth. So we use search to find the messages. We go through, this, search layer, find all the indexes that match the time range that you gave us, find all the messages that match, and then we push them through a pipeline of operators. And these operators are made based on, what you told us when you wrote the query with what's in between the pipes. There's 2 stages. The first stage will simply do one-to-one, one message in, one message out, or basically, just transform the message that's flowing through, add fields to it, that kind of stuff. And then the second stage is aggregation, and aggregation is where you start counting. And when you start counting, that's really when the analytics start. So that's very interesting as well. Some very interesting concerns there around, how much of the aggregation do you actually keep in memory versus spool to disk and so forth, because you obviously want this to be really fast. So there's a bunch of very interesting sort of heuristics at work there. And then we present the result back to the UI. And the reason why this is a streaming query engine and it's push-based is that at any given point in time, we have the intermediate results available. So we basically flush the whole thing every couple of seconds, at which point we have an intermediate result, even if we have not covered the entire query time range yet. So that's different than a classic database query, which is usually pull-based, and you don't get intermediate results. So this is sort of the architecture of the system. Those are some of the more interesting components that are in there. And then there's obviously a bunch of other stuff going on, keeping multi-tenancy information and so forth, which is really not worth talking about. It's just a freaking database, basically. One thing that we thought was very important as developers, building a service that sort of runs in a data center, even though it's through an API. This thing has to be automated. We really want to make sure that we can go from check-in, to rebuild of the entire thing, all the modules, all the applications, to staging deploy, and to a couple of other integration deploys, more or less in a push-button fashion. Again, we don't do anything that you're probably not doing either. It's just like that's what we're doing. We can't do it any other way because I can't talk to my IT guy and say, hey, can you put this CD-ROM into this server and reload the application? I have no server, I have no CD-ROMs, and I have no IT guy. So, all I can do is write code, right? So guess what I do? I write code. We write code in order to automate the entire system deploy, and then also the maintenance of the system. So we're going to talk about that a little bit more. What we are doing is we basically have a couple of stages. Night is the nightly one, and then stack is stage, and long is the longevity one, which turned out to be the second stage. And we are short on characters. So all of them can only have 4 characters. That's why they look so funky. I don't know who came up with that idea. Well, I know who it was. It was Stefan. But anyways, the Germans are taking over, I tell you. All of this is automated, but then there is also QA. So this does not mean that I'm going to check in code and it's going to go to production without having at least like one stage of verification that has humans involved in it as well. We could do that, but we don't. The automation enables scalability for us. It really has to be 100%. Just don't do it otherwise. The number of your deployments grows. You don't just have broad. It's not just that box under your under your desk that's running the entire thing. You have staging, you have nightly releases, maybe you have partner integration things, those things. If you're set up to automate the entire thing, then you will be able to scale. You will be able to do multiple versions of your own service for different purposes. And if somebody calls up and says, hey, I'm in Europe and I can't deal with the fact that all the data goes to the US, then you'll say, yay, Amazon is in Europe as well, and you just push a button and the whole thing comes up in Dublin. And then the Europeans think they're safe. The other thing that scales is your deployments themselves, what's in the deployment grows. It's a scale-out system, more customers, more load, more instances, more volumes, more everything. You can go and do this manually through the AWS console for a day or 2. And then the rest of the 10 years that it takes to get your company successful, you simply can't do that. So it has to be automated. Some statistics. We have these 4 deployments that are there's the production deployment, and then there's staging deployments that lead to production. They're running constantly. And in our case, every developer can actually make its own deployment. They can make their own little sumo, if you want, through the use of a tool that I'm going to describe further down in the slide. Each deployment has about 20 clusters. Remember, the clusters are these things that run multiple instances of the applications. The applications are made up of modules, blah, blah, blah. These are the different concerns. I showed you a couple of the concerns, but then there's obviously a couple more management concerns around that. We have hundreds of instances in production. I think we are actually in the thousands if we look at across all the deployments. We can bring up the whole thing, if the gods are with us, in about 10 minutes. And we can restart hundreds of those components on those different instances if we don't have to shut down the instances first, if we just want to push new code. For example, for a quick update for deployment in less than 4 minutes to do a full rolling thing of everything. And the way that we do this is we wrote ourselves a tool. Guess what? We're developers. We ended up writing ourselves a tool. And this one is also, it has a great name. It's very easy to pronounce. It's called DShell, DSH. We started in 2010. This was around the time, at least from what I can remember, that people started pulling, getting really interested in things like Puppet and Chef. We looked at it and we decided that the fact that, and this is probably different today, but back then it was like, hey, my recipes constantly break when I deploy them because it's a fucking scripting language and there's no compiler. And then you deploy this and the thing that sits over there is trying to make everything happen. Idempotent, as they say. Well, there's a typo in your Ruby thing, and then what do? I'm pretty sure they fixed this in the meantime. Anyways, for us, that didn't seem right. We spent about 2 hours trying it. It failed too often, and we usually do. That's the amount of research we do before we make decisions, right? So we basically said, hey, come on, we're a bunch of coders. We can write our own tool, right? We can do this better. And I still think that was actually not the worst idea. Probably would consider this, doing this again, because we can just hook out a whole bunch of different things in there. But there's a lower layer that deals with interacting with all the APIs that Amazon provides and other things that you probably can give that to another tool. But the point is that we have this, and we have been developing this, and there are people day in, day out developing on this tool for the last 3.5 years. It's model-based, and it's scriptable, and it's written in Scala. Here's a screenshot. This is a command line tool, so this is a very sexy screenshot. I'm sorry about that. The whole thing takes about 10 minutes to bring up the entire deployment. I figured it was not worth demoing that. I don't know, maybe you guys need a potty break or something, but so I'll leave it with the screenshot. What this means is that I can go on d shell, and I can basically go and look at, hey, how does my production deployment look like? There's a bunch of commands built into that, like, hey, what instances are running and so forth. I can go to my personal deployment. I can bring it down. I can start it back up again, all through this tool. Tool is based on a model. The model contains various concepts such as a deployment. There can be multiple of those. The clusters we already talked about, various AWS resources. And it's also trying to sort of make human readable names for the individual instances and other infrastructure bits. So that is actually really nice. So we don't have to, we can actually say, hey, this is the prod index 5, which in our world means that's the machine that does indexes in production, and this number 5 of, I don't know, hundreds. Just for giggles. It's actually XML. Oh boy. Don't use that for logs, please. Simple object model, as you can see. A role is really a cluster. If you are actually in this cluster, what should your instance size be? What AMI to use? And what assemblies are supposed to run there? The assemblies, that's our term for application. I don't know, we couldn't call it app, we had to call it assembly, but that just means basically something that runs our code. And you can see this basically says if you are one of the zookeeper nodes, then these are all the things you need to be running. And I'm also going to put a bunch of properties onto your file system, and I source them properly so you can have access to them, like memory settings and so forth. So that's actually pretty nifty. That's the model, and then there are multiple deployments. Each deployment is then customized by a simple properties file. So it's just like think of the model as a base class. And then you just instantiate that like a subclass, and you say, hey, this is the actual name of the deployment. And there's ways of saying, hey, my front-end role or front-end cluster should have 2 nodes in this particular case. This is the development one. How much disk should I assign to it, and so forth. And based on this, we're basically then baking the entire deployment. And the way that we're doing that is we're doing it in a differential fashion, because it needs to be pretty quick. We first find what the existing resources are. We use tagging wherever it's available using the AWS resources. So our tags are named in a particular way, so we can find out, hey, we go to this AWS account, we list everything that has that tag, and we can find, hey, these are my indexes in index boxes or front-end boxes in production. There are a couple of things where tagging is not an option, such as security groups, and there's some IAM stuff that doesn't have tag support yet. So there we just get away with basic, just a naming scheme and prefixes. And then we go about, fixing the differences in the model. So we start the missing instances, make the very different changes if there's security group missing and so forth. The tool knows how to do all of that. It has some safeguards built in. It never deletes anything. Here's an example of tag usage that's actually a somewhat more elaborate one. So tags are basically these key value pairs. This is one instance. We'll just pull that back out. In fact, what we're talking about here is we're actually talking about a EBS volume that's attached as part of an LVM set, volume set to one of the instances that captures our metadata store. That is basically our metadata store. So you can see we're pretty verbose at then putting the tags in there so we know when we look at what's actually running, even if we just use the AWS API to basically do mini CMDB. We have all of this information in there, and the tool then knows, based on this, what's missing and what it has to do. And we make this fast by parallelizing. That's really important. I mean, you can build this, and it's going to take, a year in, it's going to take 2 hours to complete. So we basically do all of the things that we can do in parallel. And we know also how to do rolling restarts. That's also important. So I said previously that the tool supports scripting, and there's no fancy model with barriers involved and so forth. We basically just tell the tool what to do and which things can happen in parallel. And if there's changes, we just update the script. So if you look at the restart -p25 of org service and all of these guys are halfway down, that basically means do a rolling restart of 25% of the nodes. So always keep 75% of them running, right? That's a rolling restart. And there's other ways of expressing that. We can say, hey, sometimes we know, go in a fixed number. So basically always bring down 2, bring down 2, bring down 2, and so forth. So that has actually turned out to be very, very efficient. So what that means is that it's actually fast enough for development. I can actually compile changes locally and push them, bounce what needs to be bounced in my development deployment in a fairly short amount of time. So nothing's happening that doesn't absolutely have to happen. So that took definitely a while to get to. And it really helps that we have a model that applies directly to us. We don't have to deal with somebody's generic model. So that's probably another reason for why doing some of your own work in this regard is useful. Oh, well, and then some usual tricks like keep hashes around and don't keep downloading stuff over and over again or uploading over and over again if you already know it's there. Only upload the change jars if you have to. Update something. We use Maven, so that means that pretty much every assembly depends on the internet. That can get pretty nasty if you don't add some smarts to it. And then we want to make it reliable as well. So no good if you have a cool tool that can do all of these things, and then half the time it runs into some corner case and breaks. That leaves you very frustrated. So there's a couple of prerequisite checks that are built in. For example, we want to make, we want to put something in a prod account, and our AWS account itself simply it's not provisioned to add more instances to it. You always have to call them and say, hey, I want another couple of hundred, that kind of stuff. So we do that, and then of course, check IAM permissions and so forth. Try to do that before you actually run any of the other tasks. So if there's anything that you already know that can fail, check that first. Fail early, basically. And then there are things like, hey, we are running out of M1 larges in one of the availability zones and so forth. So it has this all built in. This is sort of the experience that we made. Initially, it didn't have these prerequisite checks. All of these things that it does now that I mentioned on the slide, I think, are things that we literally ran into. I love that last one, eventual consistency in AWS. It's really cool. You tag something, and then you query for the tags, and you don't get that thing back. So what do? Well, you just spin. You do it over and over and over and over and over again until it comes back, eventually. So that's great. Security is a huge topic, and then it's actually one that we can do an entire hour just on that topic. But we basically use different AWS accounts. The developer accounts are obviously not as sensitive as the production accounts. This is all encapsulated. Credentials are, on, safe USB sticks, password protected, and so forth. We use minimal policies in IAM, best practices, basically. Security groups are actually baked into the model. These machines, as they talk to each other as part of the cluster, like upstream, downstream, the way that the security groups are set up are as narrow as possible. So they basically know only these other clusters are allowed to talk to them, only on those ports. So that's definitely useful. And I would recommend you do that as well. If you find out that there's something that can go wrong, add the safeguards. If there's anything that actually changes state to the worst, such as deleting something, ask first. And don't just ask for a yes with the yes being the default and the guy can just hit enter. These things happen at 3 o'clock in the morning. And the very person who wrote the tool once blew away an entire development, actually the last stage deployment, blew away all the EBS volumes for that with a fat finger. And so then we added basically a challenge. You need to basically type in the name of the deployment, in which context you're currently running, before actually making breaking changes like deletes and so forth. Again, sounds obvious after the fact. And of course, you cannot shut down prod without having some really insane kind of level of privileges. A couple of other good things we're doing there. We actually generate a bunch of SSH config with the nice names for the machines in the various deployments, so we don't have to constantly copy and paste these weird Amazon DNS names into our SSH shells and so forth. And finally, make it affordable. Developers can spin up their own deployments. So guess what happens? They spin up their own deployments. Guess what happens at night? They go home. Guess what happens to the deployments? They still run. So we wrote this thing that's called the Crim Reaper, which is probably obvious what it does. It'll shut your ass down, basically. That is really useful. I mean, you're saving real money. Some of our investors are in the audience, and I can see them laughing. So we do that. You really have to. Couple of pitfalls. Something that we have actually still a little bit to go is we use a base AMI plus a scripted installation on top of it, so the auto-scaling is not really working too well for us, of course. We like the idea that we can quickly spin the system in development. We probably should go with a full-baked AMI for production anyways. Security updates, security group updates. If you're still on the old stack, if you're not in VPC, security group updates, which we do a lot, they will potentially kill existing TCP connections. If you're wondering why your RPCs randomly start failing, then that's why. That is a hard-earned lesson, actually. Of course, there's the VPC stack as well, which is better. Parallelism can cause stampedes if your configuration data is in DynamoDB and you have read provision relatively low, because who needs to read configuration? And then you spin up an entire production deployment, or you roll one over, and suddenly 500 people need to read configuration. And guess what happens? You don't have enough read provision, and then everything comes grind to a halt. And there's also something about the tagging API. We use the tagging so heavily that we constantly hit the API limit, so you need to back off on those kinds of things. All right, so we're getting pretty close to the top of the hour. Well, I have about 8 minutes left, so I'm going to talk a little bit faster than usual. What we do is there's all of these clusters. They all have these individual applications, and they all need to know about each other. Who should I be talking to? Where's my AWS endpoint for that? Where's S3? Where's my downstream guy? Where's my message bus? The idea has always been that we start the individual application, and the only parameter that it gets is a host name. In fact, it's actually 3 host names, but let's just say for the sake of simplicity, it just pointed to a place where it can discover its configuration. And we use Zookeeper for that, and we have this concept called a service registry wrapped around it. All of our applications link against the client-side library that encapsulates Zookeeper and this notion of a service registry, where we have different types of services. Usually what happens is you say, hey, I want service X, and then it'll come back and give you an IP address and a port number. Depending on the type, sometimes there's other things, but then the call actually knows what to do with that. And we do that for our own stuff, for third-party services such as a message bus, but also if we need to talk to Elastic Cache or things like that. One other thing that we found that I thought was really interesting, because you go into this and you say, let's build the biggest freaking system we can build. It's going to scale horizontally from here all the way over to Tokyo. And then you do that, and it doesn't work. Because now, if you don't do it right, everywhere where you split load, all of your customers will be evenly split across all nodes, and all nodes at all time. So let's say these are all my indexers. This is my first customer. Oh, cool, I can scale horizontally. I'm just going to put part of the workload for every customer on every node. Same I do for the second customer, and so forth. So we have only 8 customers. There you go, I said it. Anyways, so all of your customers get partitioned to be on all of your instances. That's great, right? I mean, that's how we build software these days, scale horizontally or die. This has very, very bad side effects. None of these nodes will get enough load for any given customer, at least in a lot of our use cases, that it can actually, get to critical mass. If you think about building index shards or something along those lines, well, you got like 3 messages over here, 5 messages over there. You get too many shards, and they have nothing in them. Very bad. So what you need to do is, we call this internally customer partitioning. more load of each customer to a smaller number of nodes. So in this case, let's say we have customer 1. In terms of throughput, 4 nodes we find can completely make happen what needs to happen for this particular customer. So we'll just put them on 4 nodes. Customer 2 we put on 6 nodes because he's sending more data or whatever. And then so forth, right? So instead of having everything scale across everything, sometimes scaling a little bit less is actually more performant. Again, this is another one that looks extremely obvious in hindsight, but you need to make these mistakes sometimes to figure this out. How this actually works underneath, you can come and ask me later. I'm running a little bit out of time. Use random prefixes for key names in Amazon S3. Solutions architect told us this over and over again. Ultimately, we did it, and it actually improved performance. A couple of other things around S3. If you are using S3, Amazon.com, like a lot of libraries actually do by default, then it can actually go to Virginia or Pacific Northwest. I don't know why, but that's what it is. If you want to stay in Virginia and you don't want to have to go across the internet every time you access a bucket or something in that bucket, coming out of Seattle or whatever it is. Another very simple tip, but it really changes things. Use the explicit URL. We find in general that RAID 0 makes EBS faster. We get pretty good. We made good experiences with LVM, so I can recommend that. Snapshotting EBS volumes sounds really cool until you do it on a 1-minute basis, and you find that it completely destroys the performance. Well, kind of obvious again in hindsight, right? Like we are the kind of people who always do things, and then we get hit in the face, and we're like, oh shit, that was a bad idea. Snapshots do not always finish within 1 minute. So if you snapshot every minute, guess what happens? You're never going to be fucking able to access the data. So that's not right. So you got to deal with that. That was a very interesting one. Cost and business value, I'm going to skip over that. You need to make sure that if you expose something that works in the way that AWS works, which is beautiful, on demand, extremely powerful, if you let your developers just go after it, they will incur a lot of cost. So this Reaper stuff, it's really important. You really need to do that. Look at cloudability. Look at these other companies that are doing cost monitoring. Or raise another round. It might be easier sometimes, not always. Elasticity is, again, something that is great in principle, but it's not necessarily an arbitrary need. Oftentimes, it's, again, like the horizontal scalability. Oftentimes, your system has a baseline load. Look at the baseline load. Try to figure out over a while what's the moving average, how much compute do you actually need, and then go and buy the RIs. Again, that sounds easier than it is. It just went through this. It's easy to put that on a slide, but you have to do it. You will save money, and that's good. Okay, one more last thing. This came up in the keynote. There's this thing now called Amazon Cloud Trail, which will give you logs for the Amazon AWS API calls. It dumps them into an S3 bucket. It's beautiful. Lots of use cases, operational debugging, who turned off that server, security and compliance. Guess what? We can read from S3. We can put all of that data into our beautiful product. And we can provide really great analysis, like, where are the people that actually are accessing your resources in AWS? That's pretty cool. And other good things like that. We were actually part of the security keynote this morning. If you guys have more questions around that, please come and ask me. And that's it. Thank you very much.